For today's engineering tip, I'm going to delve a little bit into control theory and talk about a tip for when you're sketching the root locus, more specifically how to identify the break-in or breakaway points of the root locus. So typically, if you have a control system with, let's say, negative feedback, all right? So have your system. This is your open loop transfer function. Yeah, you have your system. Here is your input and this is your output. Your closed loop transfer function for negative feedback, let's say you have, let's add a k over there. Well, k would be outside, but so your closed loop transfer function would resemble this. This is what it looked like. And if you wanted to find your closed loop poles, you would have this equation, which you equate to 0. And another way of writing it is this way. So typically in literature, you're told if you want to find the break-in or breakaway points, basically the break-in and breakaway point, let's just have an arbitrary system whereby we have open loop poles and we have closed loop. Our poles, our zeros and poles in that kind of sense. So our breaking point would be this particular area. At what point does the root locus break away from the real axis to go to the zeros? So how would you get that? So in literature, typically what you do is just basically you'd rewrite this equation as k is equals to -1 all over g of s and h of s, and then you'd proceed to get the differential of this equation and equate it to 0. So that's one of the ways of doing it. The other way that is typically recommended, if let's say m is equals to your number of zeros and n is equals to your number of poles, right? What you'd do is basically you would sum up from I is equals to 1 to m, 1 all over the integral of, not integral, that's just summation of your poles and your zeros. You do have this kind of relationship. But the tricky part about this is that this zi and pi are actually the negative of your poles. So if you have your poles, let's say for instance, you have your poles, you have your zeros as -1 and -3, and you have your poles as -2 and -4. What you'd have to do when you're writing this equation, your equation would actually look like 1 over sigma plus 1. So it's the negative of the zeros plus 1 all over sigma. You're not seeing that. Over sigma plus 3, then you equate it to 1 all over sigma plus 2, plus 1 all over sigma plus 4. And then you proceed to solve this equation for sigma, and whatever sigma you get, you can use it to figure out what your breaking point is. But this can be a little bit tricky. For instance, if you forget that you have to get the negative of the zero or pole values, so you get lost. So one way of doing, and well, I'd say kind of like a relatively easier way of finding your breaking and breakaway points, which has the least amount of pain and can also give you a speed boost in case of an exam, is we go back to the one we had, the differential problem. So the differential problem was that is equal to the differential, but this time around it was -1 all over g of s, h of s all over d of s is equals to 0. Now, one thing straight away that you know is you could always, from one thing you know from differentiation is that you can always factor out a constant. So you can factor out this -1, then you simply have your 1 all over g of s and h of s all over d of s. And you simply eliminate that, basically meaning you're remaining with d1 all over g of s h of s all over d of s is equals to 0. Now, this equation will be some form of polynomial when you do the calculation. So we can say let this polynomial, let's present it as u of s all over v of s. So what you're basically doing is d all over u of s all over v of s all over d of s is equals to 0. And this is just basically, what is that rule called? The quotient rule. You basically have to do the quotient, apply the quotient rule of differentiation when dealing with this. And the quotient rule simply states that when you have d of u of s all over v of s all over d of s, it's equals to v of u of s minus prime. Let's leave out the s as u v prime all over v squared, and this is equals to 0. Now, straight away, one thing you can easily see is you can get rid of the v squared, which means you simply have to deal with, now this simply reduces to v prime minus vu prime minus u v prime is equals to 0, and this becomes u v prime, and upon which all you'll have to do now is, because these are functions of s, remember that, so you get some brand new polynomial, and all you have to do is solve for s. So if we take just a relatively simple example, let's say we have our closed loop transfer function. So just some errata that I caught while editing this video. What I'm calling the closed loop transfer function TS in this particular case is not actually the closed loop transfer function, which, as you recall from the beginning of the video, was given as kg of s all over 1 plus kg of s h of s. But what we're actually dealing with is actually kg of s. That's the transfer function that I'm going to give. So whatever I give as ts equals to kg of s, that's the transfer function I'm giving. So just to be clear, this t of s is kg of s h of s, which I am going to give as k s squared minus 4s plus 20 all over s plus 2 s plus 4. So this transfer function is not the closed loop transfer function. This transfer function is just basically the gain multiplied by the open loop transfer function multiplied by hs. You know, if you have g of s over there, your k, you know, your h of s. We really need to get better at drawing. Your r of s, like that. Alright? So this equation is actually kg of s and h of s. And if I just get into a little bit more, since I'm already here, this h of s is unity, so this is just like multiplied by 1. So remember, this is not this. Let's continue the video. T of s is equal to k s squared minus 4s plus 20 all over what's the next thing, s plus 2 into s plus 4. So all you have to do now is, at this particular point, we're not really interested in what the zeros are and what the poles are for this equation, because typically when you're using this method, you'd have to know what are your zeros and what your poles. For this one, all we have to do is expand. Of course, we know our poles are -2 and -4. Our zeros will be a complex number, 2 plus 4i and 2 minus 4i. But let's neglect that for now. So we have k is equals to s squared minus 4s plus 20 divided by, if you expand this one out, it will be s squared plus 6s plus 8. So according to this equation, all we have to do is find the derivative of the numerator, multiply it by the denominator, and equate it to the derivative of the denominator multiplied by the numerator. Simple as that. So let's start with that. Derivative of the numerator is 2s minus 4, and we multiply that by the denominator, s squared plus 6s plus 8, and you equate that to the derivative of the denominator, which is 2s plus 6, and you multiply that by the numerator, s plus 4s plus 20. So basically you have that equation that you just expand out and you have an easy time. So all you have to do is, for this method to get the break-in and break-in or breakaway points, is simply just find the derivative, multiply the derivative of the numerator with the denominator, and equate that with the derivative of the denominator multiplied by the numerator, and you're good to go. So if you expand all this out, solve for s, and you will have your break-in and breakout points. I'm not going to solve this because that's the end of it. I'm really not into it, but that's the tip. So if you really just solve it, it's much easier than working out, either directly doing derivatives or doing the whole derivative of the question, and it's less error prone when as compared to this kind of like shortcut that you've been given, because you don't have to remember, you don't have to remember about negation, and you don't have to do all this multiplication, because if you multiply this, you will come up with this same equation. And that is the end of my tip for today. This is the tip for break-in and breakaway points. So give it a try. The next time you have to do a little bit of sketching of your root locus and find your break-in and breakaway points in a relatively faster and easier method. And I think it's also easy to remember. So until the next one, cheers.